Hello. Okay, I guess we get started. So welcome. Welcome to the panel and welcome to the audience. This is a panel discussion on deep learning infrastructure challenges. My name is Jay Shenoy from Hyve. What I thought was appropriate for OCP was to get together a diverse group of people with diverse skill sets on the infrastructure challenges that we all face. And so we have Andres from Intel, who has dealt with a lot of software frameworks for deep learning in industry and academia, and he gets exposed to a lot of them. Bala from eBay has a long history of sort of SRE and data infrastructure experience, but recently he has taken on leadership of the deep learning platform. Eric Shobe, hardware engineer from Dropbox, and before that from Salesforce. So very fond of managing systems out of band. Manoj is a storage architect and many other things, but primarily in this panel, storage architect from Facebook, also an actor. And last but not least, and certainly the tallest, is Matt Singer from Twitter, who does a lot of performance testing of compute. So like different people, different companies, different skill sets. What we want to do over the next 20 or 25 minutes is to go over the sort of various aspects of infrastructure challenges. We've met as a panel before, and we have sort of decided on what we are going to sort of make sure we cover. And so basically, let me get started by saying that like when we experience deep learning as an infrastructure component, all of us end up looking at like one or two aspects, and what is lost is that like other people are sort of insisting or doing certain things because they experience certain challenges, right? And that's what we want to sort of come together and express. So each person in the panel is invited to talk for 1 or 2 minutes on a particular point of view, and then we'll take questions from the audience, and if the audience is sort of lacking in questions, then I have a whole list of questions to ask. Okay, all right, let's start with Andres.
Thanks, Jay, for the invitation to participate in the panel. I lead the AI strategy for our cloud segment at Intel's data center group, and we're driving 3 main pillars. The first one is software optimizations for deep learning for CPUs. So we want the end users of deep learning to get high performance out of their CPUs. So we have a lot of expertise at Intel in getting good performance from CPUs, and we are incorporating all that goodness into popular frameworks like TensorFlow, PyTorch, and MXNet. And in addition, we are improving the software not just to work well on one CPU, but to distribute the workload across multiple CPUs to reduce the time to train, and also to improve the inference. The second pillar that we're driving is adding new hardware features to our CPUs. So we're adding new instructions specifically to accelerate the performance of low precision, such as 8-bit or 16-bit, which is getting popularity for inference and for training. And the third pillar is we're developing deep learning accelerators, which also comes with a package of software to be able to efficiently communicate with the host, with the accelerator within one socket and across multiple sockets. And I look forward to your questions.
Hi, thanks again for the invitation. So I'll speak from a practitioner perspective, right? So I lead the AI platform, so we have hundreds and hundreds of data scientists. So what we see is a lot of diverse use cases like computer vision and translation services, classification, ranking, anomaly detection, and all kinds of stuff, right? And so they do use heterogeneous software frameworks and running on heterogeneous hardware architectures, right? So one of the things is how do we unleash innovation and give freedom, of course, somewhat bounded freedom, right? So the first challenge what we see is how do you do a good marriage between different diverse software frameworks and the hardware architectures, right? So the principle that we use is take small number of major services with unique requirements, and then we optimize the combination, software and hardware for it. Let's say TensorFlow for just GPU inferencing, for example, right, or things like that. So we pick that. What becomes also important is the performance requirements upfront is of super important while we are designing the hardware at that stage, right? And the second I would say is eBay has a pretty global presence, we have a pretty somewhat predictable usage patterns of the infrastructure, right? So one is from a scaling perspective. First of all, we need to make sure, are we driving efficiency and utilization of the deployed infrastructure, right? So we have a lot of platform intelligence like preemption or no GPU hoarding and things like that, how we drive the efficiency. And the third I would say is, because we have to watch for the fault domains and the availability zones and the different geographic locations, how we deploy. And we also have to make sure that our training and inference works, even we can take a region out, right? And also that has a lot of implications, how we design the capacity of our infrastructure. So we can go into details, but those are some top things.
Hello, I'm Eric from Dropbox. Dropbox has been one of the first adopters of new technologies in the market. So we have a lot of experience onboarding new technologies and the pain points for onboarding them. We are one of the first adopters of AMD and also SMR technologies. From looking at ML technologies, from a data center point of view, there's going to be some challenges. And when you design a data center, you really are designing for a sweet spot. And the sweet spot is a ratio of power and space. And a lot of these new technologies that are coming focused around machine learning really draw a lot more power. So there's some challenges from the data center point of view to onboard these.
Okay, thank you. Thanks, Jay, for introducing me. And let me share you something. When I saw my name on this panel, I had exactly the same thought that all of you guys have it. What is this storage guy going to do on this panel? And I'm still trying to figure it out. So bear with me if I'm going to go through my notes and try to figure out and share my confusions with you. And if something is incorrect, please blame my handwriting, because I'm going to refer to it once in a while, not my thought process. It could be either way. So I started looking at saying that the Facebook. Before I say that, let me just put it another thing. I'm 6 months into Facebook, so don't blame anything on Facebook, anything I say. It's my opinions and my opinions only. So I started looking at infrastructure for machine learning that is extremely important for any hyperscaler out there. So if you think of any use cases, search, or where you're going to deliver most relevant vertical information for that, or if you think from ad placement, if you think of newsfeed, what is the most relevant data to be provided to the users, image recognition, one after another. Just to put it in the context, there are 2 billion plus users for Facebook. There are more than 6 billion images or videos being uploaded. Sorry, 3.5. 6 billion translations per second. So all of these are most important metrics, and all they based on the data collection that you have, images or the likes or the preferences all the users have. And that is interpreted through most of the machine learning. So you can imagine this data being processed through, extracted for the information with features fed to the training coming out with model, going to the inference, and then driving the predictions. So from that perspective, now I kind of start making sense. Okay, fine, this big data is going to be fed to the training, so the big data is relevant, and I do storage. So okay, maybe there is some connection. So that's where I see what the connection is. And training is what really connects with, it's consuming most of the data. And of course, inference are driving the predictions, but a lot of that model is prepared already before you fed into the inference. So when you look at training, how it consumes, and now you're looking at how that is being done at a scale for hyperscale. So we are looking at large data centers, all the problems we do at a data center level. The data is going to be spread across a lot of infrastructure. So you're going to have not only across a lot of servers and a lot of disks and a lot of SSDs or whatever you may be, but there can also be across a lot of regions, large regions. So you want to think of now, how do you plan this? Because even though training a lot of times can be offline, so your performance requirements can be construed to be relatively lower, but they are also accessing the data, which is large amount of data, which is going to sit in the same place. Other services are running, so you can think of the SLAs, network traffic. So a lot of these are becoming real issues as we go along and start planning for the machine learning of the future. So this is where I think a lot of opportunities and a lot of challenges are and going to be there. So that's really my interest of focus, and I hope to learn a lot from the panel and all of you guys. Thank you.
Hello. I thank you, Jay, for asking me to be on the panel. I am an architect for hardware systems at Twitter. I tend to look at the ML models from the perspective of hardware, so a lot of the times I'm looking bottom up at ML models and trying to help teams design the right hardware for them and help them increase the performance of these models. And a general trend of what I've seen in the current frameworks is that engineers are getting farther away from the actual code that runs when they try to execute their models. And that's becoming a really big challenge for us, because the software engineers want to develop a model, they want it to work, but right now there's very little tooling to show them what things are in the model that are kind of performance toxic. And I'm really interested to see what people think about how do you analyze a model to find the contention points within it and to figure out how, when this is being translated into hardware, what's happening on the system, what's waiting for data, how do we make these models faster? Because I don't know, I think a lot of us see that a lot of ML models, we all love them to run faster. We don't see them a lot of the time making great use of the hardware.
So let me go through one round of questions where I ask the questions, and then I'll open up to the audience. So I'd like to pick up on what Matt was saying there and ask Andres, that you mentioned that in your observation, the software engineers are really are very abstracted from the hardware. And I wanted to ask Andres on how much of that was like the frameworks, like are the frameworks getting in the way of like performance, or is it like the developers can spend more time on the frameworks? And
yeah, so the frameworks I've provided, the frameworks like TensorFlow, PyTorch, you can also call them deep learning libraries. They provide an abstraction layer. So a lot of the deep learning scientists, they don't have to know any details about the hardware, very little details about the hardware. They just develop the frameworks, and then it is expected that the hardware vendors, such as Intel or other hardware vendors, work with the frameworks to integrate optimizations to the framework. So most developers are not writing C or C++ code. This is deep learning developers, or CUDA for that matter. They're using Python and these high-level tools. The advantage is they don't have to worry about the low-level details. Some of the disadvantages is that they are not familiar with some of the hardware aspects that can give good performance. So often they're not familiar with the memory hierarchy or that the hardware provides. But overall, from my opinion, there is a great benefit, and many companies then can work with their hardware vendors to make sure that the models that are important to them are getting optimized for the respective hardware. And also, as a hardware vendor, we go to academic conferences and try to see what are some of the types of layers of models that are gaining popularity, so that we add those to our software library.
So, follow-on question to Bala. So if developers are struggling with using the frameworks efficiently, and you mentioned that there's a very large diversity of use cases of use case versus hardware, Are we at a stage where it's possible to capacity plan at least the major deep learning use cases in a way that, let's say, a standard general purpose compute pool would be capacity planned?
Yeah, I think, so there are two pieces, right? So there's data pipeline, which is, Manoj touched upon the storage, which is a big aspect of it, because all the data pipelines have to come together. But then I'll speak primarily from the training and inference perspective, right? Yeah. So capacity planning for training is totally different relative to capacity planning for inference. Whereas on the training side, you're mostly like data throughput, right, for one of the key KPIs. And whereas on the inference side, your latency, TPS, and robustness, and those are important, right? So what we see is on the training side, again, so we have our platform that helps also to efficiently distribute the workloads across, for example, different GPUs that we have and so on, right? So from a capacity, so models, there are also different kinds, right? Some are, let's say for computer vision model that runs once a month, have more forgiving SLAs, but then there are some models that run even every 2 minutes, right? And they have to be trained and then pushed to production, right? So in that sense, capacity modeling for training, we use some preemption techniques based on like the criticality of the models, like whether it's, hey, it's a once a month, losing 10 more minutes on the model training is not a big deal, right? So that's that. On the inference side, I would say most of our inference, we plan it like a stateless application, although assisted by the data pipelines, like in parallel, right? But of course, we do have some inference on the GPU type as well, especially for image search and so on, because they do need a lot of run through like ResNet 50 to get the input image and to predict, right? So,
okay.
So it's evolving, but it's not. We're not quite there to design like stateless applications, but
which kind of explains why the demand spikes are so uneven for deep learning.
Correct.
Okay.
Correct. And one of the, for example, we have to be very careful with the capacity deployment, right? So first is like, how do you effectively utilize what you've deployed, right? Because this is not cheap hardware. Right?
Okay. So I'll skip a couple and go back to Matt. So for general compute, we are very much used to, and Bala touched upon it, latency and QPS sort of being performance metrics. How does that change for training, and how does that change for inference? And there's also sometimes the notion of accuracy and not just performance. So can you comment on that?
Yeah, I think for our workloads, latency and QPS are very important. Luckily, we have a kind of infrastructure that lets us expand fleet sizes or instance sizes pretty quickly if we need to pull latency down by shedding some load from individual tasks. On training is definitely all about the time to get the model to converge on an answer. That's the key thing. Everybody, when we have a need to train something, we have a need to get that answer so that we can put that model into production as quickly as possible.
And then how do you benchmark accuracy? Or is it possible to benchmark accuracy?
I don't think it's, we're not doing any of the low precision work, to my knowledge at this point. So I think I think we have sample sets that we can verify against to gauge accuracy, but I don't believe we've had any big issues there.
Let me skip back to order to Eric. So if like adding the dots together, so some of these machines are actually different, some of the deep learning machines are different, and capacity planning, as we heard, is maybe not so easy. And so how does that translate into deployment? Can you plan out, or do you need to plan out better your data center infrastructure?
Yeah, so if you haven't planned to onboard a new technology that has a higher power footprint, you're going to have to make some compromises to onboard that. And that sweet spot, that ratio I was talking about for actual square footage and power footprint, you're probably going to have to make some decisions on how you want to deploy this. And you're either going to have to leave some tile spaces actually open, or you're going to have to kind of peanut butter the amount of SKUs you actually fit into a rack and leave some physical space in the rack unused. And what's probably going to happen in the future when you start looking into your 3-year roadmap and planning your data center space against that to onboard these more dense racks, you're probably going to think more about the physics problems of how do I cool these guys, right? Because now you could easily jump from a 15 kW to maybe a 45 kW per tile footprint. So you're going to have to pay a lot more careful consideration about the physics of how I'm going to cool this. And you probably don't care much about how much space I have, but how am I going to cool a smaller space with that same power footprint?
So once you scale out of like a sample deployment or test deployment, you have to plan better.
Yes.
Okay. Last question from me. This is to Manoj. Is deep learning a big data problem? Is it a fast data problem? Is it both?
Yeah, I mean, in learning you have different types of workloads. So as far as the fast is concerned, it's not necessarily always fast based on the storage, but definitely big data is part of that. The question is basically how do you make sure that that big data access doesn't slow you down? So if I just think from what you're saying, right? The training models, of course, the amount of data that training models are consuming is continuously growing, sometimes almost dramatically. So definitely they're going to keep on accessing the data. So the data footprint cannot continue to expand in the data centers by just replicating for X use case versus Y use case. So you would see, I think the use case will start changing where you'll start becoming much more aware of how you can access that data more efficiently. You may start thinking of locality-based access, or you can think of application deployments which are aware of where the data is. So make sure that that big data doesn't become slow for you. Now, does that big data becomes fast data as in from access from underlying medium perspective? It depends on the use case, because training use cases, you'll see that a lot of those convergence times could be in days, weeks. Sometimes there are some relatively smaller use cases which can be in seconds too. So there are some fast use cases. So the whole data pipeline that Bala was talking about, you may see data may go through general big data to getting into the pipeline, which comes into more and more fast category as the training starts consuming it.
Okay. Audience, this is your chance. Frank?
We can repeat.
Okay. We can repeat.
So the question I have is around where you invest in optimization. So there's a set of questions that you're going to ask. I think there's two personas. There's going to be the framework owners, and then there's going to be the developers or the data scientists who are creating the workloads. What sort of questions do you ask them so you know where to invest your optimization efforts in as you're going through this exercise?
I'm just going to repeat the question also. let me take it back. So optimization, so performance optimization, where do you invest your efforts?
Yeah, what sort of questions do you ask your
developers?
Exactly.
Correct.
In order to make sure you're investing in the right area.
Correct.
So we asked both the developers and the hardware teams various questions. One of them, of course, is what workloads are important to them. So we target those workloads. But also we try to understand the capacity that the hardware infrastructure has. So for example, there's a number of customers or cloud service providers that have lower utilization during the night cycles, for example, in their data centers. And so for those cases, then we will target distributed training algorithms that they can use to scale training across hundreds of Xeons, for example, so they can train their models really fast during the night cycles when they are available. And for the other models, the types of optimization that we've seen just on one single node, for example, in some cases are 2 orders of magnitude when we've optimized the hardware, the software for their particular use cases by taking advantage of the memory hierarchy and the registers available and etc.
One more question?
Okay, so my question is about, so when you do AI workloads optimizations, I mean, they could be in 3 pillars, right? You either do it in a CPU or a GPU or GPGPU, or it could be like an ASIC, right? So in your data centers, whether it's Twitter or Facebook, how do you decide where the workload goes? I mean, is storage the driver that decides, like whether it's a CPU bound, GPU, or which? I mean, you've told us that recommendation systems is what you use a lot. So the question is maybe for you to say in which part of the pipeline do you do you intermingle it, or do you it's just one?
So there is a published paper Facebook has on that, but generally maybe I can try to. On training, you see it's a mixture, a CPU and a GPU and GPGPU in general. Inference, now this is where I think it becomes interesting, right? That these are use cases that will continue to evolve. Right? A lot of things that CPU can do really well, and some of the things that when you reach at a particular scale, those operations become really, really repetitive and has the best benefit if you start accelerating those things faster. So I think right now, maybe the politically correct answer is it's all, actually. And there are some things that exist today, and they are evolving.
I think one thing I would add is, lot of data transformations, like when you people submit Spark jobs and all that, right? So that happens on the Hadoop infrastructure, for example, itself, right? And then the transformed data that's required for the actual training part, we move either through batch or in even real time as well, right? So as far as what workloads, I can clearly say, for example, CNN models, right? Right on 100% on GPU, right? And then, but there are some very simple model, like even XGBoost or things like that. So we may run on CPU, right? So yeah, it really depends on the nature, but more and more deep learning models for sure, like RNNs and CNNs, we run on GPUs. But then data transformation, we try to do mostly on the data infrastructure itself, do the heavy crunching, and then bring the data to Hadoop cluster and then do the training part, either CPU or GPU.
So one thing I'd add is I think we've seen tremendous value in generally starting on CPU. It just really reduces the amount of time it takes you to get to understand your workload. There are lots of things you can do around getting capacity that probably is a lot harder if you suddenly want GPU capacity. So I think that we tend to wait until we have something worth optimizing and then look at a GPU.
But on the inference is almost mostly on CPU, at least today, and except for some of the computer vision cases run on even GPU for use cases. But yeah, but generally inference is totally CPU.
Okay. Any other questions from
I'll just add that on inference, I think this is where you can see the performance requirements are high from latency perspective, as well as the QPS perspective. So this is where repetitive operations accelerated can show many significant benefit also.
Okay, I think we're out of time, but we'll take one more question. Yeah. Oh, no.
Nobody told me.
No.
Get on Twitter to know about it.
I was wondering, is it because of some kind of workload pattern, or is it related to that, AI workload? I mean, which part of your ecosystem is most fragile?
Where do you start?
I love the cameras on this one. I have no clue. I thought I said I was a storage guy. I realized how much less I know. So no, I have no idea. I think this is, of course, first of all, and it will come out publicly what exactly happened at Facebook. So I'll leave out of that. As far as the fragility is concerned, I think most of the hyperscale infrastructure is based on the large infrastructure, large services that go across. Now, that doesn't mean that, of course, things don't go wrong. They do go wrong.
Okay, I think we are done. We're out of time. Thank you.